Alrighty everyone, this is Max Joyce, lab number 4, Faraday's Law 4, Physics 2212. Alright, so jumping straight into the overview, we got an introduction, we're going to talk about some equations, we're going to do the experiment, we're going to draw some conclusions. Okay, so introductions, concepts at play here is Faraday's Law, Biot-Savart Law, Newton's second law, and Lenz's law. Faraday's law is going to be the equation electromotor forces, EMF, is equal to the time derivative of magnetic flux. You add on the negative sign there, and that is Lenz's law. We see the negative sign is due to nature because nature doesn't like it when things are created. It needs something to offset it. Newton's second law, of course, is force equals mass times acceleration, which that's going to be used in a little bit when we talk about the gravitational force. Biot-Savart law is the equation on the top, where our magnetic field is equal to the magnetic constant times the cross product between V times R times the charge of whatever you have divided by the radius cubed. Remember that this is going to be a dipole, so the equation looks a little bit different. It's actually going to be mu naught divided by 4 pi times 2 mu, which is going to be that magnetic dipole moment, divided by r cubed times r hat, of course. And then the purpose of this is to understand Faraday's law using a bar magnet with aluminum foil ring to form experimental and conceptual models. Average experimental time was 1.53 seconds, and the computational model time was 1.39 seconds. Those are just a preview of the results. Alright, so this is the experiment. Essentially, we took aluminum foil, made it into a tube, and dropped the magnet through it. That's pretty much all we did. So here the system is the magnet, surrounding is everything else. So we're going to have magnetic force and gravitational forces only. Initial procedure, turn magnetic north using the phone app, measure the aluminum foil, which we'll see in the next slide, and record the dropping magnet as it falls. Alright, so here's our experimental data. Tube length was 0.28 meters, width was 0.006 meters, inner radius was 0.018 meters, radius was 0.024 meters, which we got by adding the width and the inner radius. Average time was 1.53 seconds, mass was 0.025 kilograms, magnetic dipole moment, which was from lab number 2, was 1.9 amps square amps, and then as you can see the average was 1.53 seconds for the time. Alright, moving on to our computational model. What you see in the top left corner here, this is what I just said, so I'm not going to stress over it too much. Mass, of course, is going to be the mass of the magnet, and then the mu of the magnet, which I just talked about. And then we have our next equation, which is this is our function for magnetic field. Pretty standard stuff, just using the magnetic dipole equation for that. And then if we go up here to the top right, this is our magnetic, this is our magnetic flux equation, which we used. So using, as you can see, this is kind of like all of it combined in one, so it's a little bit messy. So the numerator part is mostly going to be where you get the things for the magnetic flux. So this is combining the magnetic flux and the time derivative of it, I guess. And this is why it's so messy. But yeah, that's just the code for it. And then we have our force of gravity, which is of course just the negative mass times g, which is g is defined previously. I didn't show it because it's just a fundamental constant. And we have the ring current, which this is actually what's really important, is going to be, of course, our from Faraday's law, our electromotive force divided by R. So essentially that big equation at the top right is finding our electromotive force. And then the step 4 that you see, that's just utilizing Ohm's law. Alright, so moving on, this is just some other things, just some in-between steps where you're finding the magnetic the forces, and then we can find, from those forces, we can find position graphs and velocity graphs for the actual graph portion of this. So next I'm going to show a video. Hopefully it plays. It is not looking like it plays, so it's stuck there. Maybe it plays when I hit the next button, but we'll see. The velocity of time graph is shown to the left, and then the actual computational model picture that we got is shown to the right. As you can see, both the blue and the red ring are going to be equal in magnitude, but they're going to be opposite in the direction. One of them is going clockwise, the other one is going counterclockwise, and that's important because Of course, it's not always the same. When you drop that bar magnet, remember it's a dipole. It's not just a point charge running through there, so that's why we see both the counterclockwise and a clockwise one. And moving on to experimental versus computational. So our experimental course was bigger, computational was smaller. Error could have been from measurements, coding, timing, magnetic dipole, and magnetic north not being correct. Okay, so additional question, stronger current, meaning greater induced field and slower descent on the magnet. That's why a resistivity of the conductor is taken away. You have a stronger current, and then it does all those other things. And then if there are slots, you decrease the number of loops, which is to decrease the magnetic flux and decrease the current.